Okay, great. Thanks, Andy. So today's presentation here is on a particularly difficult tornado event that we struggled with back on Memorial Day in 2019. Usually our tornadoes out here are QLCS derived tornadoes, and I would certainly take one of those any day of the week versus on this particular day with a radar scope full of supercells that were all competing with one another and merging with other storms that really caused us a lot of heartache. So I'm going to have Kyle start this presentation off with a few introductory slides on the environment and whatnot, and then we'll get into some of the radar data and some of the research that goes along with this study.
Thanks, Todd. So before we move on from this title slide, we're coming up on the 2-year anniversary of this event. Some of the damage surveys there on the bottom, that far left one, EF2 damage to a machine shed. That center photo is EF2 damage to what was a 2-story farm home. And then the right photo, we'll come back to that one later, but that was EF3 plus damage to a trailer manufacturing warehouse near Montpelier. But if you turn to the next slide, a brief overview of what's to come. It wouldn't be a case study without looking at some mesoscale conditions. So we'll take a look at some maps from that event. We'll talk about the 2 strongest tornadoes that were within our CWA from that event. We'll also get into some scientific research as related to storm mergers and the constructive and destructive interference with that. Turn to some satellite, and then we'll also get into some GR2 Analyst to look at some of those storms as well. Starting from the top at 300 millibars, you'll see that the main upper level flow is off to our north and west across the central and northern Great Plains, but still pretty good flow here locally towards northern Indiana. Have about a 50 to 60 knot jet there approaching from the west. Stepping down to 500 millibars, you'll then notice that we have a trough digging in. It's a subtle one, but a shortwave trough digging into northern Iowa, and we're placed at a pretty reasonable location in relation to that trough. Again, plenty of flow here at 500 millibars locally. And if we step down to 700 millibars, you'll notice that the winds are now southwesterly. That is a trend that continues when we go even lower, although on this map, you can see both the closed low at 700 and now at 850. And also at 850, you can see excellent moist air advection coming in from the southwest. The flow is not especially great at this hour locally, but storms didn't get going until a little bit closer to 22, 23 Z or so. So we were able to tap into that stronger flow through some time. Also on this map, you can kind of see where our stationary front, our warm front, is actually going to kind of set up at the surface. You can surmise where that's going to be based on that dew point gradient there. Moving on down through the levels there. Here's a surface map that I did in real time for the morning. I'm a big fan of surface analysis, especially on severe weather events. We had tornadoes in this case forming in the vicinity of that warm front. As we know, fronts can be that extra oomph of vorticity that we need for tornadoes. So again, big fan of that. Otherwise, it might be a little tough to see on your screens, but our surface environment was otherwise characterized by temperatures generally in the upper 70s and dew points in the mid to lower 60s for the most part. I want to draw your attention to east central Indiana, where our surface winds at some of those locations are from the southeast. So if you, in your mind, envision what the vertical profile looks like, especially from surface to say 700 millibars, you had a nice directional wind shear in that profile, and you can imagine what the hodograph might look like for that event as well. Turning over to the next slides, which have some CAPE and some pressure falls as well. Pretty notable pressure falls. So you can see that surface low was tracking generally to the east. Once again, you get a good sense of the surface wind flow from this panel as well. The next slide, we'll get into some CAPE and some shear as well. I used mixed layer CAPE for this event here because the research papers generally tended to focus on mixed layer CAPE as opposed to mu CAPE or surface-based CAPE as well. But at this point in time, before storms were popping in our area, the Cape gradient was off to our south and west, but it was a very unstable environment characterized by easy 500 to 2,000 joules per kilogram of Cape in the area. So this is closer to storm initiation, 23Z. You can see that we are now in a very favorable, unstable environment there. And where that Cape gradient is in northern Indiana is roughly where some of our tornadoes were, especially near that that almost 2,000 joule per kilogram contour. That's pretty close to where some of our tornadoes started to form. Next slide, please. So the infamous question is you're looking at the radar capture here at this time, and you're going to ask yourself, which of these storms go on to produce tornadoes? Which of these 6 is going to produce tornadoes within the next 30 minutes? We'll come back to this and see how these evolve. But Todd, if you can show them the velocity data next, that might be helpful. Same time, same letters. So maybe think to yourself, which storms might go on to produce some of our tornadoes? We'll give you like 10 more seconds, and the answer is B, D, which the title's not correct, but B, D, and E are the ones that went on to produce the tornadic storms. So storm B, really quickly, it appears to be too close to storm A, and therefore it adversely impacts the inflow from that. And then storm B is so well removed from the supercell cluster farther south that it does go on to produce multiple tornadoes. Storm C looks to be pretty choked off by storm D off to its southeast, but it does favorably merge with storm D later on. Storm D is otherwise pretty favorably positioned and unimpeded, and it goes on to produce multiple TORs and cell mergers with that. Storm E does end up being overrun by D, and then storm D does go on to produce some of our tornadoes as well. And then last but not least, storm F, I should say, fails to produce any tornadoes, even though it's well out ahead and goes on through several mergers as well. F was definitely one of my storms. I was like, oh, it's gonna totally produce a tornado. It's well out ahead of everything, but alas, that was not quite the case. So let's take a look at the velocity data for that really quick, so you can see once again how those couplets evolved or devolved in the case of some of those storms. Let's really quick, before we get into the radar data any further, we'll take a look at the 5 tornado tracks that we had in our area. We did have 2 EF3s. Those are the ones that we're going to key in on. We had one in the northwest and then one off in the southeast. To the west of where Todd is pointing, we had 1 EF2 tornado, and then we had a pair of EF1s, one upstream of that, and then one up to the north there as well. The storms these days did go on to produce a number of tornadoes, especially in Wilmington, Ohio, their area. If you want to see their excellent write-up, you can check that out on your own time. Indy's area also had a couple tornadoes from this event as well. But the first tornado I want to focus on is going to be the one that occurred north of Macy, Indiana. It was on the ground for about a half hour. Peak winds were about 140 miles an hour from this, and it tracked for about 14 miles. Thankfully, there were no injuries or deaths from this. This tornado really did track through a very rural area. Taking a look at some of the damage photos that we had from the event, these images all come from the DAT. There were only a few interior walls remaining from the single-story home. And if the debris had been totally cleared from that foundation, we might have been talking about perhaps a different rating. The photo on the top right, it was definitely cleared, but the DAT did note that the anchoring at the base of the walls could have been improved. And that bottom left photo, man, that was one of the jaw-dropping photos to me, to see such a big transmission line like that absolutely crumpled to the ground. And Todd, really quick, how many did you say were crumpled on this day?
We had 3.
3 crumpled on that day. So this was definitely a very strong tornado that we had. So if you click through to the next slide, we'll take a zoom in on some of the radar data from that. You can see a very well-defined debris ball just to the north and east of Macy there. Very strong rotational signature there on velocity. Good CC dropout. You see the ZDR data there as well. Then the 2 right panels, we have a nice cross section to show how high our debris was, 13,000 feet just before 0Z, and then actually growing to about 16,000 feet by the time we got to 0Z and the storm matured a little bit. Turning now to the second EF3 tornado that we had, this one was on the ground for almost 25 minutes. We did have a couple of injuries from this one. I believe the scenario was a propane tank. One of the big kind of exterior ones had rolled onto a couple of individuals. This storm was also a double-digit storm in terms of track length, almost 13 miles long. We had peak winds of 150 miles per hour with this. If you look at the map, thankfully this storm was a safe distance north from Montpelier. Montpelier has a population of about 1,700 people. So we could have had a different scenario if that tornado had tracked just a couple miles south and gone through that town there. So thankfully the storm remained north of that. Looking at a couple of the damage photos, I said that we would go back and zoom in on this machine shed. So if you advance one slide, we'll take a look at the twisted I-beam that we had. Just a very strong tornado to be able to mangle what was actually a very well-built machine shed. So that was very impressive damage. If you advance again, we can zoom back out and take a look at some of the other photos that we had. The lower left was a large cattle operation. So there were lots of cows. We're talking hundreds of cows injured, and at least a couple dozen that were killed from this tornado as well. We'll zoom into the cross section on the lower right and take a look at how this storm looked on radar. Still very impressive couplet there in the velocity data. The base reflectivity is a little bit noisy, but you can kind of surmise where the hook might be just a touch off screen. You can certainly see the CC dropout as well. And then in this case, we are a little bit farther away from the radar, but we did see debris as high as about 6,000 or 7,000 feet from this tornado as well. So at this point in the presentation, I'm going to pass it back to Todd, and he's going to start to get into some of the research for us.
Okay, Kyle, thanks. So going back and doing a postmortem on this event, because we originally, at least initially, struggled with our tornado warning decisions early on in the event because we had so many mergers that were going on and we weren't quite sure what the heck was going on and what storms were going to end up actually producing tornadoes. So the anticipation on our part, at least initially, flagged what ended up happening later in the event. So one of the better operational papers that we found in our research came out in 2006 from Lee et al. And it was a really good paper done up on the 19 April 1996 Illinois tornado outbreak. In that particular outbreak, there were 39 tornadoes. They used 37 of them in their study where they had really good radar sampling. And out of those, they found 26 cell mergers. They used a methodology where they divided them up into 4 different types, and 20 of the 37 radar sampled mergers led to tornado genesis within plus or minus 15 minutes. And this event compares really well with our event, and we'll get into it in a little bit here. But historically, cell mergers have been recognized as having a significant influence on storm size, persistence, and precipitation intensity and production, dating back to as early as a paper done back in 1949 by Byers and Graham, and studied many times since. The physical processes that occur in storm mergers, however, are still not well understood. Wilkins in 1976 found that for merging pairs of buoyant updrafts, the merged pair behaves as a single updraft with twice the buoyancy of a solitary updraft. And then there was a concept proposed by Simpson in 1980 called cell bridging, which is where a new updraft growth occurs in a convergent region between interacting cells, and was observed in numerical simulations by Chin and Wilhelmsen in 1998. And interestingly, that concept was observed to be the most frequent mode of storm mergers in the April 1996 Illinois tornado outbreak. However, the influence of storm mergers in tornado genesis is also poorly understood, as shown in observational studies from our very own Mike Sabonis, who was our previous MIC in 1996, Goodman and Knupp in 1993, and Wolf et al. In 96. In the Illinois event, of the 26 mergers that were identified by Lee, 58% of those were owing to differential cell propagation, and another 27% owing to differing cell speeds. Finally, 8% were from differential directional propagation, and another 8% from flanking line cell supercell mergers. So the four categories that we proposed, what he called type A, which is where a larger cell incorporates a smaller cell, and there's no recognizable new cell development, reflectivity area expansion, or intensification of the primary storm. Then there's a type B, which is an interaction between a dominant and a subordinate cell, where the reflectivity of the dominant cell pulses upwards, and or reflectivity development occurs on the periphery of the dominant cell at or near the point of merger. Type C, which is a development of distinct reflectivity maxima between the two merging cells in close proximity. This is what they refer to as the bridge cell between the two original reflectivity maxima. And we had this occur in our particular event. And then type D is a distinct cell growth at or near the point of coalescence. Again, in the Illinois study, 20 and 37, 54% of radar sampled mergers led to tornado genesis within plus or minus 15 minutes of the merger. And a little over half of those was within plus or minus 5 minutes. And Kyle will get into this a little deeper, because there was a good follow-on study that came out after this Lee paper in 06 from Jarrett Rogers down at the Storm Prediction Center. And he used the same kind of methodology and expanded it over a 5-year time period based on SPC's storm database. And he has some really interesting results that he's going to share here. So I am going to now get into a little GR2 Analyst review here. So if I go back and you remember that quiz slide, what storms were going to produce tornadoes, this is pretty much the starting point of that image that we showed. And I want to point out here on the radar screen here, we've got a series of supercells aligned pretty close to the position of the warm front. And the question is okay, which ones are going to end up producing tornadoes? Because earlier in this event, for the previous about hour and a half, we had struggled with several supercell storms up here in Northwest Indiana. They had good rotational couplets. They were in a good environment interacting with the warm front, but yet none of them produced any tornadoes. And as you can see here now, starting at this particular point, and this is where we started to anticipate a little bit better, and going forward, we did much better as far as the tornadoes that did actually develop in this event. We only missed one, and that was the start of one of the tornadoes, but we grabbed a hold of it pretty quickly thereafter, and we did okay for the remainder of the event. So I'm going to start to loop this forward. I want you to watch the interaction up here between these two existing supercells, and then note this small cell down here to the south of the supercell center near Rochester, Indiana. And I want you to watch what happens when this merges with this particular supercell, and then what happens with the rotational coupling. So I'll advance this forward here slowly. So there's the merging cell. And right there would be the point where they would be considered to be merged together. That's at 2340. And then you can watch the circulation come together very rapidly. And boom, right there we have a tornado right northwest of Macy. It looks like a little debris ball in reflectivity, and that is only 8 minutes later after the cell had fully merged in with the supercell. Now, if you transition and look up to the north here, what's going on between this supercell and this supercell in close proximity to one another? And this is another little interesting deal here that happens. We were watching this storm really close thinking, okay, this thing's probably going to produce a tornado, but then the conversation between the radar operators was like, hey, I think this is having a negative influence on this guy here. They're in too close a proximity. And sure as heck, something happens here. It's probably a case where precipitation into the inflow region of that particular supercell resulted in an increase of the mixed layer inhibition, reduce the buoyancy and weaken the overall updraft and the circulation. And you can see that happen as I advance even further. In fact, the storm ends up falling apart about at that point there. Meanwhile, down south, after that merger, there's the Macy tornado that continues in progress. It does begin to weaken though with time. You can see there's a fair amount of precipitation that's spreading through the inflow region of that particular storm. But then again, there's also another merger that occurs, and the storm attempts at least to spin up another tornado, but it ends up failing, and then it weakens quickly with time by that point there. So now we'll transition down to the south. We'll go back and look at that storm D again that was embedded in that larger area of cells right back here. Now, as Kyle said, Storm E, which is right here, did produce a tornado south of Peru, northeast of Bunker Hill. It was pretty close to right there when it produced. There is some interaction occurring between this larger storm off to the southwest. I loop it there for a little bit. You can see the influence there. And then those two, that storm actually kind of gets absorbed into the larger supercell off to its southwest. Meanwhile, we go back down to the southwest again, Storm D. It's going to produce a pretty good tornado off to the east here. Watch this particular cell off to the southwest that ends up merging about right in there. And the circulation very rapidly intensifies, producing a tornado right here northwest of Sweetser. That's when it started. And then it carries eastward. Now, from this point here, things get really messy. I'll roll it back to about this point right here. You can see Storm D kind of, at least at that point, fairly well separated with storms off to the south-southwest. There's a developing supercell right here over towards Galveston. And I just want you to watch what happens here as we go eastward in this interaction between these two supercells and this new storm that's coming up from the southwest that merges with that what we call Storm D. And I want you to note how the circulation kind of reforms. So this is a case where combination of these three events, the merging cell, the upstream supercell, there's a cell bridge, which is taking place right here. I don't have composite reflectivity to show you here, but there's a new storm that bridges in between these three features here and results in the circulation rapidly reforming underneath, and then it quickly develops a tornado. This is that strong EF3, almost EF4 intensity tornado that then ends up tracking north of Mount Pillier. And then finally, old storm, if Kyle, you can set me straight. I believe this was F. So F was sitting up here all by itself. We thought for sure this thing was going to produce a tornado. We had indications of strong circulation at several points in time, but eventually it ends up decaying. But it's interesting to note that it never actually produced a tornado. Now, why is that? Perhaps this is a case where anvil seeding from supercell storm D on the inflow region and the updraft of storm F prevented a more intense updraft and a more intense circulation. So that's our speculation there, but I don't really have anything that I can definitively put on top of that. So that's my GR2 review. We'll go back to the slide deck here, and then I'll let Kyle take over with the additional research that we used from Jarrett Rogers from the Storm Prediction Center.
Okay, so moving back into the research. So Jarrett Rogers, like Todd said, carried on with where Lee et al. Kind of left off and expanded this into a 5-year look at EF2 or greater tornadoes. So of the 718 tornado reports, 669 cases were examined. Some of them were thrown out because of either poor radar coverage or uncertainty in the quality of the reported tornado start time or the location, or kind of little nuances of that nature. So of those 669, just shy of 200 reports featured a cell merger in those cases. So that turns out to be about 27%. So if you think about that, in one hand, that's a pretty fair number of tornadic cell mergers, but there's also several that did not. And we kind of talked about that with Storm F. It looked pretty good for a time, but then just didn't quite pan out that way. So turning to the next slide, Rogers did classify the storms into 4 different categories. We had discrete cells, which are pretty easy to imagine. Then you had a cluster where you have a storm embedded within a disorganized group of storms. You had a broken line where you have discrete storms embedded within a well-defined but discontinuous convective line, so kind of not quite the organized line. And then the line, of course, is defined there on the slide. That one's pretty straightforward. Now, I mentioned this slide because these 4 classifications are then talked about on the following slide, in which Rogers takes a look at, okay, here are the different types of cells and which ones had cell mergers. So you'll notice that discrete cells were the most common tornado producing storms. And overall, that's not terribly surprising if you kind of think about some of the things Todd was talking about, such as storm inflow and those interactions. So, but also cell and cluster is another fair number, but really the discrete cells are going to be the ones that you want to watch for tornadic cell mergers. But once again, keeping it in perspective, there were also a fair number, if you look at the gray above that, that were some of the significant tornado reports that were not the tornadic cell mergers in there. So this next chart here is really going to be my favorite. Like Todd was talking about, our mergers, our tornado reports relative to the mergers occurred within 10 minutes or less, and that's exactly what this chart is explaining here. You'll see the 0-minute mark in the center of the x-axis, and you have a wide range, 15 minutes ahead of the merger, all the way to about 10 minutes after the merger. Once you get beyond 10 minutes of the merger, you can probably relax your trigger for the tornado warning. It's probably not going to happen, at least based on this case size. But if you look at the large number of mergers that happen, immediately before we see it on radar data, that tells you that either we're not scanning quite fast enough on the radar data, or that these storms are interacting, well before we even see the merger come together there on radar. But we definitely had our tornado cases here meeting this time on this chart. So turning to another set of research, this one had to do in part with anvil shading. Admittedly, this paper gets pretty technical pretty quick. So the methodology, very briefly here, the group is going to be modeling of a supercell and how it is initiated. And then they're introducing these boundary layer rolls that are both going to be perpendicular to the cell motion or parallel to the storm motion. And then they define what these boundary layer rolls are specifically in that quoted text there. But I want to get a little bit into some of their conclusions, and they did consider some of the impacts of the anvil cirrus, such as, you know, what's the ice content of the clouds, how much radiation is being let through. They did a number of simulations to kind of explain these. And of the 5 conclusions, I think 3 of them are especially applicable to this scenario here. So direct quote here from the first conclusion: when boundary layer convection and cloud shading are included, the magnitude of sin increases, whereas CAPE and the LCL generally decrease in proximity to supercell thunderstorms, largely due to the storm-induced effects of anvil shading and compensating subsidence, end quote. So that one's pretty straightforward to understand, where, you know, all of a sudden, if you have this big anvil coming through, you're going to start to, you know, decrease your instability. Sin's going to increase, and then lower the LCL there as well. Their second conclusion that I think is relative here reads: low-level shear increases in proximity to supercell thunderstorms, largely due to low-level inflow acceleration of the storm updraft. The extent of this updraft and its influence on storm relative helicity depend on the base state hodograph and shape. So in that regard, that's something that we can also surmise from some of this case, where you can see some of that rapid spin up in the proximity of those supercells. Then the last conclusion I want to share with you: shallow cumulus clouds in the inflow region are suppressed near the storm, regardless of anvil shading, owing to a region of compensating subsidence around the main updraft. So when we get to some of the satellite loops, you will see at some points fairly steady shallow cumulus clouds trying to get going. So then for that conclusion, you know, they're going to be suppressed regardless, because of the compensating subsidence around the main updraft. So in a perfect world, you know, we could play with this Meso2 data up close, just like we did with the GR2 Analyst. But in this loop, you can see, as Todd mentioned, to start this event, we had some pretty potent storms near Lake Michigan there in the far northwest Indiana. But eventually through times, you'll really start to see those overshooting tops get cranking in a north to south oriented line across northern Indiana. And if you watch towards the middle and end of the loop, if you watch toward northeast Indiana, you can see a well-defined overshooting top. And that was probably with that tornadic storm that was just north of Montpelier, because that was a really, really potent storm that moved through there. The next images are infrared satellites, so you can see the cloud tops as we lose daylight there, just a different perspective. So if you think about kind of anvil shading and how that might impact either positively or negatively, there was definitely a lot of cloud cover around. So in some regards, it's almost amazing that we had as many tornadoes as we did. But just kind of putting a bow on the research, there's a lot of research that still needs to be done, because you know, we need to look at maybe some null cases on why it didn't work. We could really use some up close kind of Doppler on wheels type analysis to get a good sense of what exactly is happening, because there's definitely a lot of positive and negative interactions going on in these scenarios. So turning down to our last slide here, as I said, research is complicated. We have to keep going on the research, and I suppose that there really is going to be no shortage of you know, cell mergers in the future. It's kind of the atmosphere that we work with. It's a fluid, right? So Todd's idea was, hey, let's get this onto a Vortex 3 type field study. That would be pretty sweet. Pretty confident that the roll tornado was a result of constructive interference, but you know, for the instances of constructive interference, in the Rogers case, for example, you had about a third that were constructive and had tornadoes, but then you also had a fair number that were where there was destructive interference. So that's certainly a play in some of our null tornado producing supercells. And especially here in the Midwest, if you're listening, beware of those frontal boundaries. Those always tend to provide the extra oomph that we need. So Todd, let's move on to the reference page in case anyone wants to grab a screen capture of that. But I guess now we can field any questions that the group might have. So thanks for being here and thanks for your attention.